Hello, my name is Sebastião Moura and I am working to get my master's thesis in engineering physics. In today's day and age, people's reliance on physical money has been dwindling, and we have become increasingly dependent on electronic payments, most notably with credit and debit cards. As our methods of payment evolve, so too do the security requirements of these systems. However, with more advanced security come more advanced ways to exploit the shortcomings of this security. Every smart card has an underlying electronic system. These systems consume power, which means that there will be a current variation, which can be measured by placing a resistance in series with the smart card and measuring the voltage drop at the resistance terminals. This is called the leakage of a circuit, the measurable physical behavior that depends on the data being manipulated by the device. A static current is related to the magnetic field through the Biot-Savart law. As the current passes through an infinitesimal piece of wire with a certain orientation, it will contribute to the magnetic field at any given point, with a dependence on the distance and orientation of that point. By integrating this expression along the wire, we can calculate the total contribution to the magnetic field at any point. Unfortunately, the current in a circuit is not static because of variations in time. However, the Biot-Savart law is still valid if the field is measured near the source, aptly called the near field. This holds for measurements near the source without getting too close, where we would reach the reactive near field, where the magnetic and electrical fields would be too complicated to model, because at this distance, the probe itself could radiate back to the source, interfering with the measurement. Since the elements of the circuit are near each other, fields generated in the circuit can couple with each other, resulting in modulation. Modulation is when a periodic waveform, called the carrier signal, has its properties changed by a different signal, which usually contains information to be transmitted. This principle can be used to take other known signals, like the clock signal, and discover information which is modulated inside this signal. It has already been observed that there is a statistical dependency between electromagnetic emanations and the values calculated by a device. And this allows attackers to discover information from a device. By recording the electromagnetic leakage from a circuit, designated as a trace, over several measurements, while calculations of interest are happening inside the circuit, we can obtain information on how to unencrypt the data we are looking for, such as a PIN code. These kinds of electromagnetic attacks were studied at Universidade by an IST student, Ricardo Massange, in his master's thesis. In his experimental setup, an inductive probe was used to read the magnetic fields created during smart card activities, obtaining the traces necessary to discover the smart card code. The challenges now are to read all the electromagnetic activity with much better spatial resolution. In my thesis, I will develop smaller, more sensitive magnetic sensors using spintronic sensors. In particular, I will use magnetoresistive sensors based on tunnel effect, microfabricated with few micrometer dimensions. Many different spintronic sensors are being developed at Universidade, and hopefully, one of them will help improve the results obtained from electromagnetic attacks on smart cards and help improve their security, allowing all of us to sleep safer at night. Thank you for listening, and I hope you all find this topic as interesting as I do.